All right, hi everyone. So I'm just before lunch and we are late, so I'll try to make things faster. And so my presentation won't be very technical. It'll just be more or less of an overview of what we have done in this field. And the main idea is to sort of introduce you a little bit to this idea of stowage planning. So David has been really nice in presenting what liner shipping was, which I was counting on. Thank you. So I'm not going to do that. But what I'll do is that I would like to take you a little bit away from what is like strategic or tactical planning of looking at networks and look into what can we do at the operational level. I mean, as things are now, can we do something about making our operations more green? So here is a little bit of an example. It's not precise, but it gives the idea. So if you have a service like this, going from, for example, from Tangent Pass to Rotterdam, you have some working hours that you have to have at the port. So you have some loading and discharging operations. And if you're sailing at 21 knots, you can make the journey in 17 days. Now, if we are able to reduce the time we spend at port, then all of a sudden we can still manage the time windows of our customers, like David was saying, but we can actually reduce the speeds, thus making the journey longer and more green, and still be within the customers. So what I'll show you today is how can we actually do that? Can we reduce the time at ports from a liner perspective? So usually every time we talk about time at ports, it's from the terminal. It's what the terminal can do to make things more efficient. But what can the liner actually do? So I'll give you a little bit of a background so we are all sure that we understand what words I'm saying, and I'll give you this overview of what has been done in stowage planning in this regard, and then a little teaser on what can be done in collaboration with the terminals, and then I'll conclude. All right, so a little bit of background. I assume all of you know what a container is. Maybe you don't know that there are different sizes of it. So you can have, usually standard is 20, 40, or 45 foot longs. Some are slightly higher. Some containers are refrigerated containers, so you can use those, for example, for shipping pharmaceutical goods, tank containers for dangerous goods. You have flat racks like this, which don't really fit within a container structure, so you can have like yachts or trailers. And then there goes the container ship. So the container ship obviously is where we want to put all those boxes, and we'll always think that this is something easy to do. They're just all in standard sizes, but just showing that there are actually very different ones of them. So when you have to stow like 18,000 of them, like in the Triple E, that is not an easy task. And just to let you know, so I'll be talking about bays. So a bay is just a section of a vessel, and it's divided between an on deck and below deck. You can see a picture here. So this is on the deck. There is a it's called a hatch cover. It's a metallic structure, so you can have containers below and on top. Okay, then a little bit about terminals. So this is the terminal in Aarhus, actually. So the place where you actually let all the containers is called a yard, and this is the quay side. So this is where the ship actually comes and you have all your operations. The gate is down here where the trucks comes in. Interesting thing I'll talk about is the vehicles running around the terminal. So this is, for example, a straddle carrier. It can run through those rows of containers and just pick them up and bring them to the cranes. You can also have trucks running around. It depends on the kind of terminal you have. But anyway, you have vehicles running around. Then you have the big cranes, the key cranes, which are actually the ones that are used to move containers on and off the vessel. Okay, so now that we have all the terminology in place, well, there are two players here when we talk about time at port. One is the carrier, and the other one is the terminal operator. So the carrier knows what is the release, so what are the containers that are on the vessel that needs to be discharged. It knows the tank content, so the vessel has a number of tanks, and that defines what the condition of the vessel, what that is. And then you have the terminal operator, which knows what's the load list, so what are the containers we want to load on the vessel, what are the available cranes and vehicles, and what's the status of the yard. Status of the yard is simply knowing, okay, those containers which I need to load, where are they in the yard? Because depending on where they are, that's going to change the distances between them and the cranes. So what happens is that you have the carrier is starting to do a stowage plan. So stowage plan is simply deciding where containers should go on the vessel. Now, if you want to make that efficient, you have to make sure that it fits with the cranes that are available at port. So the stowage plan needs to know what the terminal does. So what are the cranes and what are the vehicles and how do you schedule them in order to make it efficient? The terminal, on the other hand, it needs to know what the stowage plan is in order to make the crane and the vehicle and the scheduling of the vehicle efficient. So those two operations, they're sort of interdependent. Usually, what we do in academia is we take those two problems, we put them together, we make a bigger problem, and then we have years and years of research on how to solve those problems, which works so long as it's the same owner of the problem, which is not the case here. So let me tell you a little bit about those two problems aside, and then we'll dig a little bit into what can be done together. So here is a ship. Here you have a pair of cranes. This one here represents the yard, and what we have up here is the number of moves that needs to be made for each of the bays. So we have a number of containers to unload, a number of containers to load. The cranes start up at some position, and then you have the vehicles running around, picking up the containers and bringing them to the cranes. Now, let's focus on the cranes themselves. If we start with the cranes like this, well, some time goes on. We could, for example, after 120 moves, we have that the first crane finishes, and if you notice, there is not really space enough. There is no physical space enough to get this crane to move over to the next bay. So what happens is this crane has to wait for the next one to finish. Now some more time comes in, and now finally we can move the cranes, and so it goes on. Again, this one finishes first, it has to wait again, so we are having those delays at the port. Now we could avoid that by moving this crane one bay aside, but you might notice that, well, if we take the number of moves here, that's 180, so this one will not be finished, so we'll have this crane moving over here, and not being able to move to the third, so it's going to be wait again. Well, here is another example. In this case, we actually can move a little bit faster, and the last crane at some point finishes. It has nothing else to do, and we have a little time there. So it's extremely important to know how we have to plan the scheduling of the cranes. Now here is another little problem. So this is O's, and the A10 service from Maersk sails through here. What that service usually does, it picks up a lot of reefer containers full of pigs for England. Now, the reefer containers are over here in the yard in O's, and then a few of them are there. Now, when the Maersk ship comes in, then this port has to do around 1,000, 1,500 moves of containers. All those reefer containers don't fit in here. So a few of them actually get stored on this side over here. Now, when I say that a vehicle has to bring a container from here to the key crane, which is usually over there when the Maersk Triple E comes in, it takes 3 minutes to do this operation. Now, if you plan it wrong, what happens is that you have 2-3 vehicles picking up the containers here, getting all the way to the key crane and having to wait because the other vehicle hasn't come yet. So if you don't plan, if you don't schedule your vehicles right, you're going to have delays in front of the key crane as well. Okay, so all of this is basically decided, all this scheduling and all this vehicle scheduling, it's highly dependent on how we arrange the containers around the vessel. And you do that by doing a stowage plan. So let's have a look at what it means to do a stowage plan. So when we do a stowage plan and we decide where the containers have to go, well, as we just have seen, the ship comes in and we want to make sure that we distribute the containers along the vessel so that all the cranes, they can work in parallel and they can work efficiently. Then we want to avoid unnecessary moves. So This is what in stowage planning you call over stowage. So here you have a green container that is getting off at the current port, and the red container is getting off at later ports. Now, as soon as we get to the port, we need to remove the red containers in order to get to the green one. It gets even worse if the green container is below deck, and you have to remove all the containers on top because you have this hatch cover that needs to be removed as well. So that requires a number of extra moves, so those you want to remove. And you think about it, okay, but I mean, there are boxes. Sure, you have a big ship and you have to put in a lot of boxes, but how hard can it be? Well, let's see how it is. So here is a piece of a bay. Well, first of all, you want to make sure that if you have refrigerated containers, they have to be where there are reefer plugs. So where there is electric plugs, otherwise the refrigerating unit won't work. And there are not that many of them, and they're usually at the bottom. You have to make sure that the weights are within limits, otherwise we make holes in the vessel. We don't want to do that. Well, there is a hatch cover below deck, so when we put containers in, we don't want to hit the hatch cover. If you remember at the beginning, I told you a few of the containers are called high cubes, so it's slightly higher. So if you put too many of those, you'll hit the hatch cover, so you don't want to do that either. If you have dangerous goods, well, you have to be careful on how you arrange them on the vessel. Because some containers cannot be together with other containers, and it depends on the kind of goods that is in there and how they react together. Like fireworks and heated tanks, they won't go together. If you have containers on deck, well, you have to lash them together. You have to tie them together, and that requires also a number of complicated calculations in order to make it work. And if you're able to do that for 18,000 containers, well, then you also have to be careful about the distribution of the weights all along the vessel, because those weights are different. Each container has its own weight. So what happens is the vessel might tilt a little bit depending on how you distribute them, and then you have differences between the distance between the water and the keel, the bottom of the vessel, in the front and in the back. This distance is called the draft. Well, trim is the angle you're in. Well, you want to make sure, for example, if you take the draft at the back, that it's deep enough so that the propeller is actually into the water. You might also want to make sure that the trim is a specific point, because the vessel are designed with a specific trim to sail as efficient as possible. So you might want to do that as well. Some ports are not deep enough, so you can't load all the containers you really want unless you're going to scrap the bottom. Well, once you've done that, if you look up at the laws of physics, you also have some forces pushing up so that the vessel actually can float. Those forces change depending on where you are in the vessel, because the vessel is not a box shape. Now, subtract those forces from each other, you get some resulting forces. And if you take a vessel like this, and let's say that each of those sections that I cut, they are independent. And what happens is that if the resulting force is positive, meaning that you don't have much water, those will float more. Otherwise, they will sink more. Now, this can't happen on a vessel because they are not independent. So what happens is that you have shearing and bending moments on the vessel. So you also have to make sure that all this is in place. And you have to take all that into account while still trying to arrange the containers so that they are efficient as possible for the terminal. You want to make sure the vessel is stable. So this is called a metacenter, and this is the center of gravity. The metacentric height, it tells us how stable it is. If the metacenter is below the center of gravity, we're going to capsize. If it's too high, then what happens is the vessel is too stiff. So when a wave comes in, it rolls back too fast, and the containers on top, they fly off. So all that is something you need to take care of. And it's extremely difficult to do to solve a problem like that, and it will be even worse to try and put this into that problem and solve everything together. Aside from this, you have the carriers. They don't want to share information with the terminals because, well, I don't want to tell you what's my capacity. I don't want to tell you what kind of containers I'm going to load in the next ports, and so on. So it becomes also difficult there. So What we did was that in 2009, we started a project with the Danish Maritime Fund. That was the logo at that time. And we looked at the state of the art on stowage planning, and so that you could solve very, very few vessels on oversimplified problems. So all this discussion I've given you about stability and key cranes and all that, it wasn't there at all. There is a work from Kim and Kam where they actually started working on a little bit larger vessel, but it still had a lot of simplifications. So what we did is that we devised a way, we figured that you can't have a mathematical model that solves it all. It's just too big. So we divided the problem into two parts. The first one is called a master planning, where we take, so here you have the number of containers to be loaded on the vessel at current port, and then you have a forecast of what's going to happen in the next ports. So what we do, instead of deciding where each container has to be stowed, we decide how many containers in which part of the vessel should be stowed. So we sort of give a layout of how things should be like, and that's what we call a master plan. The important thing is that if you look at this solution over here, you can see maybe this is the port where we have the most complicated planning to do. So if we now at the current port, which is this one here, we make a stupid mistake, which could be easy because you don't have maybe don't have that many containers to load on the vessel, that might have a very big impact downstream. Once we have done that, we take the solution from the first port and we do what we call a slot plan. So we look at each of those containers we decided to have in the vessel and we decide the exact position. At the same time, we figure out that all this stability stuff could actually be linearized. So all this stability measure, they come into what is called a hydrostatic data table. If you plot it out, that's what it will look like. And we figure, well, actually we can linearize this using planes and piecewise linearization, and we have a very big model and some graphs showing that our linearization is actually good enough. And now all of a sudden, we are able to solve a number of stowage planning instances in about 10 minutes. And here we're talking about large vessel, up to 12,000 containers. If you look at the major contributions, I think the most major contribution is that this has inspired the work that Rune is actually making. So there is a company developing a stowage planning tool. There is almost already out there. So the models can actually be used, and now you have a way to help the planner produce stowage plans that can actually reduce time at port. During the next couple of years, we haven't had a very strong focus on this, but we worked a little bit on making this, the solution methods faster and more reliable. We started up some collaboration with other universities, and we figured out that there is still not much work that has been done on stowage planning. Now, if some of you have ever looked up at articles, well, Google Scholar is a good place to do it. If you look up to stowage plan, then you find that there are about 960 papers that show up. I think about maybe 100 of those are relevant. Most of them are how to pack a container. If you look about vehicle routing, then you get 75,000 hits, most of which will be relevant. So why no one cares? And the reason is probably because there is no data available anywhere. It's extremely difficult to get a collaboration with the industry and get them to tell you about this problem. So we started up a new project this year called DynaStow with the new logo of the Danish Maritime Fund. And what we did here is, first of all, we tried to stop what is called inapplicable applied research. So in the past few years, I've seen a few papers on stowage planning coming up with extremely simplified models. And I was like, why anyone is still working on this? Well, obviously data is not available, so they do what they can. But what we did is that we took one of those simplified definition of the problem. We did a column generation-based approach, and we proved that you can solve those problems to optimality. And we proved that if you take the benchmarks that are available out there, they are ridiculous because they all have an objective function of 0. So we hope that this work will sort of set a stone and say, okay, you cannot work on simplified stowage planning anymore because it's not interesting. So that was the first thing we did, and we made a benchmark available, which is actually a little harder. So if you do want to work on this, then please work on this benchmark, which actually is difficult to work on. Done that, what we are looking now is, staying from the liner perspective, is how can we optimize time at port without knowing anything about the port? And the liner came up with this idea of a crane intensity. So, as I was telling you before, a crane can work on one bay, but it cannot have another crane working on the other one. So at least it has to work on 2 bays. So if you take the amount of work on each of them, and you take the biggest one, you get what is called the make span, the minimum amount of time you have to work. If you take the total number of moves divided by the longest crane over this make span, you get what is called a crane intensity, which is some kind of measure of how many cranes you want to use. Now, you can use that as a target. So if you know that at this port you usually get 4 cranes, you can impose 4 cranes as a target and try and optimize the make span. This turns out to be rather difficult with the mathematical models we had before. So all the nice thing we had before suddenly collapsed because we can't solve the models anymore. So we are doing a little bit of research on how we can save this and keep the mathematical models with all the nice linearizations and try and find a way to solve this crane intensity planning problem. Another thing we have ongoing is that we're working on the forecast. Now, this forecast is usually pretty bad. So you have a huge number of no-shows, especially if you're going through Asia. So you can have up to 50% of no-shows. So you have a lot of uncertainties in the data. And, well, our models, they are trying to have the vessel being stable all the way along the trip. But does that make sense when most of the data is wrong anyway? So we are looking into how we can take this uncertainty into account and make robust models so that when we sail from the first port, even though things change along the way, it will not be a problem. And now for last, let me tell you about a new project we are just starting up. We did some preliminary work, and it's together with the APM terminals in O's. And this is where we are trying to get those 2 parts to work a little bit together. I don't know, you probably read the news about the split of Maersk, and there was something that was really interesting. They talked about that they're going to be an integrated transport and logistic company. So I had a few guesses of what that will mean from my side, and I think it will mean that we'll see more door-to-door kind of services, focus on that, focus on reliable and efficient services, and a huge need for cost-efficient operations. Because no one cares about the cost of transportation, no one wants to pay for it, it has to be there on time, and the only thing we can do is make it more efficient. And Maersk Line and APM terminals, I believe, will be the key players in this kind of company. Now, if you're at a terminal, and this is your vessel with a stowage plan that tells you container A and container B has to go here and here. Now, this is where they are placed. It will take you this amount of time or this distance to move those containers. Now, what if I could tell you that those 2 containers are of the same type? And by type, I mean a container that has no importance for the liner. The liner doesn't see them as being different. So they have the same discharge port, they have the same, more or less the same weight, and they have the same revenue. So the liner doesn't really care whether A and B are in those exact position. We could actually swap them around. And in terms of cost, it will be exactly the same. But if you look what it means for the terminal, it will have a huge impact because now all of a sudden I can put B over here and A over there, and the distance will be shorter, which means time at port will be smaller. If you would allow the terminal to have a little extra flexibility, you could even let them decide on how to load the schedules, load the containers on the vessel. Now, most of the small terminals, for example, they do what is called a sea to land policy. So they start from sea, they build up the stacks and go towards the land. And that will give you some measure of time. But if you allow it to actually optimize that sequence, then you will be able to improve the time it takes. You could do things like, if I have a container like in O's that is going all the way to the second reefer yard, well, maybe I can fit in a couple of containers while the long travel is being done. So this new project is supposed to look at this ship loading problem. We divided it into a number of sub-problems, you could say. So we have the operational stowage plan. So if a shipper comes and he tells you, I have those containers, this stowage plan, well, you're allowed to change containers of the same type. So you have some kind of assignment of containers. This is what we call the operational stowage plan. You have the load sequencing we just talked about, and you have the equipment assignment and scheduling. So in the project we have right now, we do assume a sea-to-land policy, simply because it's already complicated as it is right now. So this is, we'll add it later. And we're looking into a limited number of vehicles, and we'll do the scheduling of the cranes. We're not going to do the vehicle pooling, which is what it's done in automated terminals. So a vehicle will be assigned to a crane, and it will remain on a crane as you would do with the main vehicles. The state of the art completely disregards the vehicles, meaning that they assume that there are enough of them, which is never the case. So the current work is that we have a mathematical model which is available, and we are almost done with a fast heuristic implementation for it. So we'll hopefully soon come out with some results that we'll be able to show. Adding vehicle pooling will be interesting, especially if you're talking about automated terminals, which will be the case with the APNT and MASK, and the use of buffer areas, where you actually allow containers to be dropped underneath the key crane and be retrieved by the key crane along the way. Okay, and then just to conclude, so we almost make it on time. If anything that you have to remember from for all I've told you is that as things are right now, we can make our service more green by reducing the time at port. We can do that by stowage planning. We can do that by helping the terminals, making the schedules better for the cranes, and we can even boost it even more if we allow some collaboration between them. And that's it.
Thank you. Questions from there?
Yes.
So that's right. So when a ship comes to a terminal with a stowage plan, the kind of swapping you're talking about is actually allowed. So terminal is allowed. So when a storage plan is not, you don't have an actual ID on the containers, right? So they're allowed to do that optimization. But I think when the industry talks about exchanging information, where the situation is exactly the way you say, it's actually also about that the terminal knows about the storage plan more ahead of time than it currently does, and that the line of shipping in return knows about the expected situation on the yard more ahead of, well, actually they don't know anything right now, but at least the number of cranes, because normally a contract would be like, the number of moves over a particular period. It wouldn't even tell how many cranes to expect, which is all you need for the crane split. So anyways, so there's definitely something going on here, but the actual swapping is still allowed. And they also normally have a weight window in which you can do that, and then the more tough the line of shippers are, the less window they give you, maybe just plus minus 1 tons, the most tough I heard about.
Yeah.
And the least tough is there's no storage plan at all, just do whatever you want.
So when I talk with the terminal over in O's, that is done where they have an agreement. Unless their agreement is in place, it's mainly just they'll try it and they'll call the liner and say, could we do this change? So it's not a given, as far as I understand at least. And it's true, if you go to IPM terminals, even the operating system that they have does something similar to that. is completely out of their hands. They don't really know what's going on. It just does it. They have no idea whether it's good or bad, and don't really know what's going on behind the scenes anywhere. And in terms of data, that's kind of a delicate situation because they do have a lot of data. It's a matter of the problem is how much can they actually use, or are they allowed to use? I know they use more than they're supposed to. I often say no to data because I know that I shouldn't get it, and I don't want to be in trouble. But
you said in your new project the first task was to stop all irrelevant research, but on the other hand, you were complaining that no people are doing research on stowage planning. So don't you need some easy problems as entry for people to come in, and then they will make more advanced models?
yes, but I think it makes sense to do easy problems which are complex to solve. But if you have so my biggest complaint is that you have a very simple problem where everyone is focusing on heuristic methods. But the problem itself, as they define it, and the data that they are using, is not an optimization problem because all the solutions have a value of 0. So you could just transform it into a feasibility problem, and that will be that. So you could add a constraint that says there is no overstowage, and you made everything easier, and then it's done, right? Yeah. So that I don't think it makes sense to work on heuristics on that. So if you take the new benchmark we made, then it would make sense to look into exact methods, and I would see that would be helpful. But heuristic methods, I don't think that will make sense. It'll be. I mean, if you have to do a heuristic, do it on a much more complicated problem.
But my experience is that the amount of people working on heuristics is much bigger than the people working on exact methods. So if you want to make a big community of people working on these problems, then you also need something which is applicable for heuristics and somehow easy to implement.
And that's why we're doing a new benchmark with where we're trying to create a vessel that looks like a real vessel. Because I tried to get one, but I was not allowed. Yes.
As I understood, the storage planning is the exclusive toy of the company, the shipping company. There is no. What they're trying to get is some kind of interaction with the port, but right now the decision maker is the captain of the ship or the shipping company.
The decision maker is the carrier usually. I think if you take smaller carriers, sometimes do let the terminal actually do the storage plan, which I think it's probably the case with Genova, with some of the smaller carriers there. So it depends a little bit on who they are, but if you take a liner, then they usually have officers doing storage plan and nothing else.
The swap that you discussed with these identical containers, doesn't that affect the unloading as well? Because now you made it simpler to load, but then you might have made it more complex to unload, or?
Unloading is usually not too much of a problem because you already know where they have to go. I mean, the containers are already on the vessel. So the ones you are unloading are already in the vessel. You can't change them.
Yeah.
And usually the position of where they're going in the yard is already been decided, or is decided as soon as you pick the container. So there is not too much optimization to be done there. And in terms of stowage plan, there is much more optimization to be done in terms of where to put them in the yard. But the operation itself, it doesn't have a lot of flexibility there. Okay. So even if we do a swap here, of course it might have an impact on the unloading on the next ports, but that would mean making terminals talk to each other. That would be even more difficult.
questions. Thank you.